Okay, so one thing I do want to mention about okay, because I looked it up, so then I do it. Okay. Okay, I'm gonna go back to the parsec. So the definition of parsec. Okay, so you do have the sun here. Where's your sun? And if you look at basically the orbit of Earth going around here, so let's say the Earth is over here. Actually, I need a bigger picture. And here's your sun. Let's say the Earth is over here. So from here to there, this is 180. That's the definition of 180 there. And let's say we have way out here, we have these are really going to be like distant stars. Okay, so if you're here, if you move back and forth like this, those stars are so far away, you're not even going to see those moving. You're going to appear to be fixed. Well, let's say we have them a relatively nearby star. And what's going to happen here? If I'm over here, so I'd have this distance here. So this is going to be some distance here. And I would basically measure from here to there, and I'd have something over here like that. And I could call this is going to be theta here. And then we have a circular orbit for the most part, so this is also the 180u. And then we're going to get the same angle over here, theta. And this is going to be over here like that. Now, the reason why I put it here is that these appear to be fixed. Okay. And so if you look here, you're going to see this star basically in a fixed background over here. Over here, you're going to see the star in this fixed background over here. That's why you can actually measure this angle here, theta. Because that angle is going to be, you can, which you'd actually probably measure, this angle here when you take half. And what you do is that this distance from here to here, you define this to be 1 parsec. Okay, let's say when theta is 1 arcsecond. Okay, so when this is 1 over 300 and 1 over 3,600 degrees. When this is a case here, this is then by definition 1 parsec. And I did not realize this until I looked it up. Parsec stands for basically parallax of one second, meaning 1 arcsecond. So parsec. And this means a parallax of 1 arcsecond. So you get the par, and then you get the sec here. That's actually where that's coming from. So what do you have here? Well, you have S equals R theta. So if we do S equals R theta, okay. Well, the R is this part, the S is this part here. So this is your 1AU. Your R here is your 1 parsec. And then your theta here is basically the 1 arcsecond. I guess you have to use, that's the 2 marks on it, right? Arcsecond. Yeah, something like that. Now, what do you have to do? You actually have to convert this into, so what you have here is you really have 1 parsec here. I'm just going to circle, you can see this. Be 1 over 360 degrees here like this, then times pi over 180 here like that. You would put in the 1AU here. The 1AU I looked up before is 1.49 times 10 to the 11th meters. Like that. And so your 1 parsec is this 1.49 times 10 to the 11th times 360. It's 180 over pi. Okay. And when you work this out, this ends up being approximately 3.26 light years. Okay. So that's formally how you define a parsec. Now, in principle, these stars out here have will have a parallax too. But why don't you measure the parallax then for these?
Saying those two
small. The parallax angle is going to be remarkably small. And this is actually kind of interesting. Okay, so people will poo-poo the Greeks. They'll say, well, look, the Greeks thought that the Earth is at the center of the universe. How stupid they were. No, there's actually a very good reason why the Greeks knew that the Earth had to be at the center of the universe, that the Earth had to revolve around the sun. What is it? That if you had this, what would you observe? You'd be observing parallax. Okay, and right, if you'd have this part here, you'd have this part here, but when they looked at the stars, they were not seeing any parallax here. So that's why they realized that the Earth had to be at the center, because if you're at the center, you're not going to notice any parallax. So when they were looking at these stars here, they weren't noticing this. If you're at these, right, because these stars would be like this. And so if you looked at the stars from here, and if you looked at the stars from here, you'd see these stars actually shifting from one to the other. And so that actually was fundamental proof that basically the Earth had to be at the center here, but the Earth cannot rotate about the sun because they observe no parallax. Okay, fundamental proof. Okay, and that's completely correct reason. Okay, but there's an assumption. What is the assumption? Why would that even fall apart?
Stars are close enough to the angle of the parallax.
They assumed that the stars are close. They had no idea that these distances were gigantic. But as soon as you put in these distances are gigantic, that parallax will occur. It's just so small you're not going to be able to measure it with the naked eye. But that was actually the mistake in the logic, is that they assumed that the stars here are actually very close. Just I think that makes sense. So they actually had very good reason for why the Earth had to be at the center. I just had a wrong assumption in a different part of the argument. Okay, kind of interesting. Okay. So with that said, and as far as the data is actually very hard to get. I think one of the the story basically about how Kepler used the data from Tycho Brahe and then it came up with Kepler's and so on, but I looked toward some of the planets and stuff like that. Have you ever seen that data and how he took it? Actually, Josh Thomas has actually one of the labs. He has the lower level astronomy students do. He actually uses the data that Tycho Brahe had to actually calculate the Jupiter elliptical orbit. Now, how did he take it? Basically, he was in a chair, and he was able to like measure angles sitting in this chair. Okay, like that's going to be accurate. Well, evidently it was accurate enough because first of all, if you look at the data for basically the orbits of the Earth or for Mars, they're almost perfectly circular. I mean, if there's your sun, you don't quite get this, but you get something, not slightly off from the sun. I mean, if I were Kepler looking at the data, I would just assume that Tycho Brahe had made a mistake. Like basically you're getting circular orbits. Because that data is not far off from being circular. But he had enough confidence in Tycho Brahe's ability to take measurements, and I don't know how, considering how it was taken. I didn't realize that you have electrical orbits. Okay, with that said, let's go back to our argument. So we tried to come up with the metric that we're going to need, and we wanted the universe to be homogeneous and isotropic, and then also spherical, though the spherical part is not necessarily the case, but we're going to set one up for a spherical case. And just I know Junior had made a comment. He says, well, doesn't isotropic imply homogeneity, or homogeneity imply an isotropic system? And it doesn't necessarily. Okay, so this is kind of answering Junior's question, but Junior, you can watch the video. So this is just a note. Isotropic does not imply homogeneity, and vice versa. Okay, so let's take a case of something that is purely homogeneous and not isotropic at all. Okay, so again, what does isotropic mean? The x, y, and z directions are
The same.
they're all the same. Okay, and so very and just you're gonna basically when you have something has some sort of anisotropy in it, it's going to depend on the direction and the angle. But what you can do is you can have a perfectly homogeneous system. So here's something that's homogeneous. I can have just basically like a vector field. That is perfectly homogeneous. It doesn't matter where I am. I have this perfect vector field like that. Is that isotropic? No, absolutely not. So this is not at all isotropic. Then you can have something that's isotropic. Okay, but it's not going to be homogeneous here. And again, what does it mean to be homogeneous?
Looks the same.
Look, it's going to be, and it's going to be basically no matter where you're at, it's always the same. So here, where I'm at, it's always the same. So I could have actually imagine like a density profile like this. Or actually, you can just take something like this, where actually. Let's just, yeah, I'll just. Just the electric field for a point charge here. So in this case here, it's isotropic, right? If I go in this direction, it's all the same. Okay, or I could have imagine I have like a onion, and I have the density in the onion kind of varying as you go out. Okay, that's going to be basically that'll be a case where it's not going to be homogeneous because the density is varying, but it doesn't matter what direction I go, it's always going to be the same. Does that make sense? So they don't necessarily imply the same. So they're going to be homogeneous. So no matter where we're at, any spot in the universe, it's just like any other spot. And at any spot, the x, y, and z directions are all the same. Okay. So that's just to kind of answer Julie's questions. Okay, so that said, let's recall what we did. So recall. We set up our spherical homogeneous isotropic model by starting with a circle. So we had this 2D case. Here's a circle like this. And what do we want to have happen? Well, we want this. We're going to assume Euclidean geometry. Let's say a flat metric. Assume a flat metric. We call this here A. And then what did we do here? Well, we said then for a circle here, we know that x squared plus y squared plus z, not that equals a squared. We beat on this, and what did we end up having? We ended up with this ds squared equaling a squared times d theta squared. Once we convert that. Okay. And what does that mean here? Again, theta is the distance this way, and then if I'm here or here or here or here or here, it doesn't matter where I'm at. It all looks the same. That makes sense? It's the same in any direction you're at. So we said, well, let's go to the next step. Let's go to 3D case and look at let's say the surface of a balloon. And so then if we did the 3D case. We'll call this here A. So we're going to assume that our ds squared is some dx squared plus dy squared plus dz squared. Again, for a sphere, you'd have x squared plus y squared plus z squared equals some a squared. We can take this, solve this for z, put it in here. Could write this in terms of the x and y, so we'll reduce this to a two-dimensional problem. And then we said that this x is going to be your a cosine of theta. And our y is going to be our a sine of theta. And then what that reduces to is this. This reduces to our a squared theta squared with sine squared of theta d phi squared. Didn't do that at all. Let's do the whole thing. Sine of theta cosine of phi, sine of theta, sine of phi. Where z is an a cosine of theta. Now it reduces to that. What's that? Did anyone look that up?
I
Okay, if you haven't, it's toward the end of the semester. I can't. Plus, I didn't read it up. I dumped it on you at the last minute, which is moderately unfair. But this is what you're gonna get. And so what do we have here? We now have a two-dimensional problem. We're on the surface of the sphere. And on this here, it doesn't matter where you're at. But I could be here, I can be here, I can be here, I can be anywhere on here, and it's gonna look exactly the same. So now we're gonna extend this to the next, we're gonna basically go to the 4D version of this. To get our model that we really want for our problem. Okay, so if we go to the 4D case, okay, it turns out I'm not going to draw the 4D sphere. I'll leave that as an exercise for yourself to do. But what are we going to do? We have basically this ds squared equals dx squared, plus dy squared, plus dz squared, plus dw squared. This is not time, again, we're only looking at the spatial piece yet. We're only looking at the spatial piece. We have that, and so we have to ask, well, what would then the sphere be? Well, the sphere would really be the following. It would be an x squared plus y squared plus z squared plus w squared. Okay, equals w squared. Okay. And then what do we have here? We have that this w. Well, I could then do say 2x dx plus 2y dy plus 2z dz plus 2w dw equals 0. I can also say that this w is the square root of a squared minus x squared minus y squared minus z squared, like that. We can put that all up in here. Well, actually, I'll just if I solve this for the dw one, this dw here, well, this dw is negative of all of this divided by this w here. So you don't want this such here. That. And if we do that, that gives us this yes squared here. Here goes this guy. And all those minus signs are going to go away. So that's going to give us this x, x, y, c, z squared, all over a squared minus x squared minus y squared. So now what do we have? Now we have a three-dimensional problem here. Does that make sense? Now, is everyone going to be happy? I'm going to just clap my hands and declare something to be thus. Okay. So what you can do, you can say x is not going to be r sine of theta cosine of phi. Y is going to be r sine of theta sine of phi. And z is going to be r cosine of theta. Now that's the same as we did last time. What's the difference here now?
using R instead of A.
We're using r instead of a, and this r is going to be now a variable. It's not going to be fixed anymore. The a is fixed. A is this dimension. This a is the radius of our four-dimensional sphere. Okay. What we have here is this part here is now just another coordinate. Okay, I'm going to clap my hands and claim that if you take this and put it all in here, you're going to end up with the okay, where's just I don't have the And I have the handout I gave last time from Whitey. That guy. So that's it. I left you coming. It's gonna end up becoming his equation 59. So if you do that. Okay, I'm not gonna make you do this. Because once you do this to your case, you're gonna see that there's not gonna be a whole lot other than it turns out this gets a lot more hellacious because you're gonna get a triple finish draw here. So you're gonna have really, really nasty things, and I think you have better things to do with your time to the end of the semester than squaring these all out. But if you do that, you end up with this dr squared over 1 minus r squared over a squared plus r squared d theta squared plus r squared times theta d phi squared. Does everyone have with me just clapping my hands and killing a bus? Okay. Like good. Now this term right here, this 1 over a squared, sometimes that gets classified to be k. There's going to be some weird definitions we need here. This k here is basically related to the curvature. Okay, because a here is what your radius here. So if your radius is really, really big, what would your curvature be? If you had a really, really big sphere. No. Yeah, right. If you're on it, right, let's say we're on a big sphere called the Earth. Okay, the R is actually quite large, and what does it appear? It appears like we're running flat. We're basically our world is flat. But if you had a very, very small radius, then this would appear. You'd actually appear to have an actual curvature. Okay. I think I ran to be for about the level first before, so I won't have the random level. It doesn't mean my level random level first, right? Before I think. Yeah. We're below. Okay, when you take French, as well, because the grammar is actually somewhat simple. You read the little French. That's a painful book. It's painful in French. It's painful in English. Sometimes it's remarkably painful. It's always considered this great classic. Fine. But the little Prince is on these little worlds, and the little worlds are like yay big, and he's like this big. So the little Prince at least realize he has curvature. He's on a place with curvature. That's the only redeeming that. That hurt. That was one of those novels you read, not even a novel, but you read it and go, wow. So what can we do with that? Now let's put this all together to get the model that we're going to have. We're going to tinker with this a little bit more today, actually longer today. So our model. For our universe. So remember, we started off with this. And what did we do? We're using co-moving coordinates. So any point is basically going to represent the location of the galaxy. We're assuming that on a big enough scale, basically everything is uniform. And we're assuming that basically those galaxies are not moving because basically the space is expanding itself. And so, and we're also going to use proper time for t, and I'm just going to call it t. So your tau is t. So it's going to become this. It's going to become this minus dt squared. We're in natural units here. We gave Ohanian's argument for why the time position curves are positions are 0. And then what are we going to have here? Now we're going to have this ds squared. I'm going to call this spatial. Okay. This right here is going to be the spatial piece. Okay. So this guy right here That's gonna be, here, but we're gonna do one little modification here too. Okay, what did Hubble show? That the universe is expanding. So the way this is always done is that in front of this term here, there's gonna be another term put in here. And what you call this is varies depending on what author you have. I want to use Carol's notation because I'm going to switch over to Carol's discussion here. He's going to call this R squared. So what we're going to do is we're going to do this. Well, we're basically putting in this term by hand. We're putting in this capital R here. This is Carol's notation, the function of t. And he's making it squared, isn't he? He's making it squared. Okay. Times basically this piece over here. This t, the r squared. 1 minus r squared, a squared. Actually, he's calling it kappa. He has not called it anything yet. Okay. I'm just going to put this in. Plus this r squared. Yeah, squared. Okay. And what this is accounting for the expansion. Okay. Does that make sense? So basically, here's a nice spherical universe here. What's happening here? Basically, it's getting bigger and bigger.
Wait, is that the same thing as the cosmological constant?
No, that is not. Now, what's going to happen is we're going to relate. This is going to change. And the question is, why is it going to change with time? And the cosmological constant will play a role in how it's changing with time. Okay, so we're going to find out, we're going to get the dark matter, we're going to get regular matter, we're going to get the photonic matter, and we're going to get then dark energy, which is your cosmological constant. And they're all going to play a role in basically how this is actually changing with time. And this is going to, the mathematical shape of this is going to change with time. So it turns out that early in the universe, the photons are going to dominate. So we're going to have the photon realm. Once the universe gets bigger, then it turns out the matter dominates. Then we're going to have, so this would change in a different way. Matter starts dominating. And then it turns out that as the universe gets bigger and the density of matter then decreases, it turns out what you still have, you're going to have this constant term from the dark energy term. And that's going to then dominate. Okay, so when we're going to plot actually how this is varying with time, but we're not going to call it like we're going to go through a series of name changes to get this. Does that make sense? Okay. Questions with that? Now, what I want to do is I want to get this from another argument. In other words, okay, this is actually the argument there that Hanging gets for this one. That's actually probably my favorite argument, is that you can actually kind of see my tiny brain can comprehend that. Sphere, 4 dimensions. Solve for W, insert one, crank. I like it. My tiny brain comprehends that. The other one's a little more esoteric, and it's actually a very good argument. But I want you to see both of the arguments. So what I only want to do now is I want to basically do another argument to show how we're going to get the exact same result. Okay. And Ohanian does this argument too, doesn't he? I don't think it does. But, so let's use another argument to show that this ds squared spatial order is this dr squared 1 minus r squared over a squared that's r squared dr squared. Okay. So what are we going to do with that? We're going to do a number of things for this. Where's the best place to start? So in general, what we're going to do, we're going to say we're going to have this. We're going to say the spatial part. here is going to equal, instead of writing it like this, what Carol does, Carol's actually going to call this gamma here. He's going to call, I'm just going to use this notation. That's really kind of stupid notation. Okay, he's going to call it gamma ij dxi dxj, because again, we're only looking at the spatial piece. I would just continue to use the g here itself, but since I'm using his notation here. So this is just like g, but it's only the spatial parts of g. Okay. So the question is, if the universe is isotropic and homogeneous, what must the R what does he use for the notations? Okay, he's using IJK. You know, IJK tensor look like. Okay, and he puts a little 3 here on this right here. He puts a little, is it on this side or does it do the other side? And he puts a little 3 here with a parenthesis here like that. I think I'm going to be dropping that notation almost immediately. And all this means is he's just looking at the 3-dimensional version of the Riemann curvature. Okay, and he's loaded this in X here because it's immediately working. Okay, so the question is, what's the most general version you can have of this, assuming that a universe is isotropic and homogeneous? Now, most people will just write down the answer of what this has to be. And what I'm going to do is Ohanian, if you look at the thing that I handed out to you, Ohanian gives a better argument for why this has to be. So I'm going to modify Ohanian's argument. So this is going to be, we're going to use basically a modified, slightly modified variation on Ohanian's argument. Okay. So let's say we're using a locally flat metric. So if you're using a locally flat metric, basically what happens, your G would become basically your is. Okay, so and locally, well, actually we don't even need that right now. If you have this right here. We know that this can't depend basically on, it can't depend on direction, it can't depend on location here. The question is, what does this have to be here? You'd have to have some constant. And then what else would you have to have? Let's see, what kind of objects do we know that are going to be somehow tensor-like, but are not going to vary with location or direction? And it's really kind of, it's going to be very obvious since this point. The Kronecker delta. Okay, right? The Kronecker delta does not vary where you're at. So I can say, if I can have some constant, I'll call this K1. And I just have all these indices here. So I could have a Kronecker delta with I and J. And then what would I have to have a Kronecker delta with then K now? That has to be general. So I can have another constant K2. Then I can have a Kronecker delta, I can have this I here, but now this I can then move K. And then that leaves in a Kronecker delta with J then and now. Uh-oh. And then I should have a K3 here. And then this would be the Kronecker of what?
IL.
Not L, and that leaves Kronecker.
Okay.
Okay. Makes sense. Now, what do we know? If I have this, if I take these two and switch them here, what do I have? I'm gonna have the exact same thing about my J and K are gonna be switched. So this would become K1 JL KL plus K2 JL J. I'm sorry, I'm trying to know JK J K IL plus K3 JL I. What else is this set equal if I switch these two?
The negative of the first one.
I switch the negative of the first one. So this has to be minus RIJKL. So if we do that, what does it mean here? Well, this guy matches up with what one? Yeah, this one matches up here. Okay, was that going to be negative itself? No. The only way to actually have that K1 would have to be. Yeah. So this one right here, this means that K1 equals 0. Now this one here, what does that match up with?
K3 on.
This one over here. Now if I look at this combination here, in order for those to match up, obey this minus sign here, what do we know about K3 and K2?
Minus each other.
Has to be minus each other. This means that K2 has to equal minus K3, and you get the same result from the ideal. If you look at that one here. So what this means here is that our RIJKL is really going to be so I'll call it K2 delta JK. This is set JK. JK delta IL minus K2 delta. Ooh, yeah, I extracted the wrong one. The top line. Delta IK delta JL minus K2 delta IL delta JK. Makes sense. Now, okay, imagine we're at K2. Okay, we're just going to call K2. Okay. We're going to left. Okay. What we have here is this RIJKL. I mean, this is that three-dimensional thing. I think I've already dropped the 3 because I'm tired, but we need K delta IK delta JL minus delta IL delta JK. Okay. And in a flat space. Okay. In flat space, this is what? This is just really this right here. In flat space coordinates. Locally flat. Okay. So in general, if I'm not locally flat, what is this going to become? I'm not going to have eta here. I'm just going to have the g's. What's going to happen here? Just have this the G, JK, G, JL, that's G, IL, G, JK. Most folks will just state this without giving any plausibility argument for it at all. They'll just state the following. If you look at most proofs start they become ridiculously esoteric. I think actually Ohanian's argument here is actually the cleanest one I've seen. Actually, what I can follow about, oh, yeah, this is coherent. Okay. So this is going to be this one here. This is often, if you look at the literature, this is called the maximally symmetric. So this is maximally symmetric. meaning it's isotropic and homogeneous. Okay. Well, let's do a little bit more with this. If I raise up my I, okay. So how do I raise up I?
G,
G,
I,
but where would my I be?
top.
Would be the top. Okay. So do you mind if I just raise this up? Look, this is not getting work. Is that fine? So I'm gonna say that now we can write. Actually, I'm just I'll keep it with what it is. No, I'll keep my G's. And how do I then get my how do I get this?
Over I and K.
I saw over I and K. So this becomes that there. What does this from here become? Something on these. This I becomes a L. This really becomes G, J, L. Now, what is this? This is this guy here, which is
One.
oh, that's 3.
Yeah.
Because you're still getting all the X, Y, and Z values. So this gives you 3G J L minus G J L equals 3K G J L. What would R be? Oh, okay, minus 8,000 for the professor. Have a problem with this one here?
2, 10.
I think 2 maybe is a little something. Yeah. So what is R?
The
Close.
6K.
It's 6K. That makes sense? Because what do? You basically raise this up, then you sum over them, right? This is your R, L, and this is going to become 2K GLL, which is the same thing. This is 2K delta LL, which is your 6K.
S A B C.
Okay. So what we want to do now is figure out what else would this be here. So we're going to write the metric in another way, way that's going to be very, very familiar to you. And then we're going to tie it back into these results. We're going to basically recover that same that we had from the O'Hadian segment. So bring this sheet. We're going to move it next time. Bring this sheet, and then also bring the one from Carol. We're going to need that as well.